Hello everybody. In this video we are going to be taking a look at the solutions to the honors mirror homework problems 11 through 15. Let's take a look at problem 11. A solar cooker, which is really just a concave mirror pointed at the sun, focuses the sun's rays 18 centimeters in front of the mirror. What is the radius of the spherical surface from which the mirror was made? So I am given the focal length, which is 18.0 centimeters. I am looking for the radius of the curvature, and I know that the radius of curvature is simply 2 times the focal length. So 2 times 18 centimeters will give me a radius of curvature for this solar cooker of 36.0 centimeters. Problem 12. How far from a concave mirror with a radius of curvature of 23.0 centimeters must an object be placed if its image is to be at infinity? Remember that an object is at infinity on a concave mirror when the object is at the focal point. So when the object distance equals the focal length, then the image is at infinity and no image is formed in front, or no image is formed in the mirror. So if my radius of curvature is 23.0 centimeters and my object distance is at infinity, I know I need to find the focal length. And the radius of curvature is 2 times the focal length, so the focal length is going to be half of my radius of curvature. Half of 23.0 centimeters is going to be 11.5 centimeters. So the object distance has to equal the focal length, which is 11.5 centimeters. Problem 13. At an intersection of hospital hallways, a convex mirror is mounted high on a wall to help people avoid collisions. The mirror has a radius of curvature of 0.550 meters. Locate and describe the image of a patient 10.0 meters from the mirror. Determine the magnification of the image. So in this problem, I have my radius of curvature, which is negative 0.550 meters. I have the object distance, which is the patient, of 10.0 meters away from the mirror. I am looking for the image distance and the magnification. To find the image distance, I do need to know the focal length, and the focal length is 1/2 of the radius of curvature. So what 0.550 meters divided by 2 will give me a focal length of negative 0.275 meters. Remember, it is negative because my focal point is behind the mirror, because it is a convex mirror. Now that I have the focal length and the object distance, I can use the mirror equation to find the image distance. So, rearranging my mirror equation to solve for image distance will give me this formula right there. And when I plug my values for the focal length and for the object distance into that equation, I am going to get an image distance of negative 0.268 meters. To find the magnification of the image, I just simply take the negative of the image distance divided by the object distance. So my image distance is going to be negative 0.268 meters divided by 10 meters will give me a magnification of positive 0.0268. Problem 14. To fit a contact lens to a patient's eye, a keratometer is or can be used to measure the curvature of the cornea, the front surface of the eye. This instrument places an illuminated object of known size at a known distance, which is our object distance from the cornea, which then reflects some light from the object, forming an image of it. The magnification M of the image is measured by using a small viewing telescope that allows a comparison of the image formed by the cornea with a second calibrated image projected into the field of view by a prism arrangement. Determine the radius of curvature of the cornea when the object distance is 30 centimeters and the magnification is 0.0130. We have our object distance, 30 centimeters. We are given the magnification, which is 0.0130. That was an awfully wordy problem just for two givens. Sorry about that. And we're being asked to find the radius of curvature. So to find the radius of curvature, I know I need the focal length, and I can't find the focal length from just the object distance and the magnification. But from those two things, I can find the image distance. So to find the image distance from the magnification and the object distance, I want to use one of my magnification formulas. Solving that for the image distance will then equal the negative of the magnification times the object distance. So plugging my values for magnification and object distance into that equation, I will have an image distance of negative 0.390 centimeters. Now I can use my mirror equation solving for focal length. And solving that for focal length with my object distance and my image distance inserted into that will give me a focal length of negative 0.395 centimeters. The radius of curvature is 2 times the focal length, so 2 times negative 0.395 centimeters will give me a radius of curvature of negative 0.790 centimeters. Problem 15. A concave spherical mirror has a radius of curvature of 20.0 centimeters. Locate the images of objects distances of, the first one is 40 centimeters away. In each case, state whether the image is real or virtual, and upright or inverted, and find the magnification. We're given a radius of curvature, which is 20.0 centimeters. And from that, I can find my focal length. I know the focal length is half of the radius of curvature, so half of 20 centimeters is 10.0 centimeters. And I'm going to be looking for the image distance. So for an object distance of 40 centimeters, using my mirror equation, and I want to solve my mirror equation for the image distance, and I'll get that version of the equation right there. I plug in my focal length of 10 centimeters and my object distance of 40 centimeters, remembering I always have to take the reciprocal of the sum of my reciprocals, and doing that will give me an image distance of 13.3 centimeters. To find the magnification, I take the negative of the image distance divided by the object distance. So the negative of 13.3 centimeters divided by 40 centimeters will give me a magnification of negative 0.33. So my image is going to be real because I have a positive image distance. It will be inverted because I have a negative magnification, and it will be reduced. My magnification is less than 1. Part B asks us to find the image distance for an object distance of 20 centimeters. So again, using my mirror equation, solving it for image distance, plugging in my value for the focal length of 10 centimeters and object distance of 20 centimeters, that will give me an image distance of 20 centimeters. To find the magnification, again, it is the negative of the image distance divided by the object distance. Both of those distances are 20 centimeters, so that will give me a magnification of negative 1.00. So once again, my image is real because I have a positive image distance. The image is inverted because I have a negative magnification. And the image is unmagnified. My magnification is 1, so it is neither enlarged nor reduced. Part C asks us to find the image distance for an object distance of 10.0 centimeters. Once again, using my mirror equation solved for the image distance, I am going to plug in my focal length of 10 centimeters, my object distance of 10 centimeters, and when I do that math out, my calculator gets mad at me because I get an answer that is undefined, which means that my image is located at infinity, which I know happens when the image distance and the focal length are the same, or I'm sorry, when the object and the focal length are the same, or when my object is placed at the focal point. No image is going to be formed on a concave mirror. So there is no image formed from this object placed at the focal point.